Now, the last topic that we talk about in the gas law chapter is it deals with real gases. So we've been dealing with everything that we call an ideal gas, and mainly the two major things or the couple major things that an ideal gas has is that the gas particles don't take up any space and the particles don't interact. There are no intermolecular forces between them. And again, that's ideal, but we live in the real world, and so real gases actually behave a little bit differently. Now, the thing about it is when we worked in the lab, these ideal gas laws worked pretty well, and that's because under typical conditions that we find ourselves, the gas laws work well, and the approximations or the assumptions we make regarding ideal gases also work well. However, under low temperature and high pressure, that's not the case. Okay. And one other thing that you might have been wondering about or worrying about, or maybe you hadn't even thought about it, and I understand that completely, is how come all these gas laws, regardless of what they are, Boyle's, Charles, the ideal gas law, etc., they work no matter what the identity of the gas is. And that's because an ideal gas, it doesn't matter if it's a really heavy gas or if it's a really small gas or if it's a really polar gas or if it's a non-polar gas. That doesn't matter because the ideal assumptions that we make take care of that. Okay. Now, when we think about this, again, the major thing, volume of individual particles is negligible compared to the total volume. That's true. Okay, we assume that they don't take up any space. They take up some space, but compared to the distance between particles, their size is very small. Okay, we also assume there's no intermolecular forces. Okay, but these ideas or these things do not work when we're under high pressure or low temperature. And so if we think about this, PV over RT equals N, that's from the ideal gas law. And so 1 mole of gas, PV over RT equals 1. Okay, but as it turns out, we don't observe those types of conditions at high pressure. So you can see a number of different gases. So at ideal gas is the purple line, and the number of moles isn't going to change based on this expression. However, at high pressures, there are lots of different things that happen. Okay, and so the main point is that under high pressure or low temperature, gases are not going to behave ideally. Okay, and again, it has a lot to do with interactions and such. And so again, there are interactions in terms of real gases. Okay, and you could think high pressure, it makes sense that these things are not going to behave ideally because at high pressure, the particles are pushed really close together, okay? And therefore, they're forced to interact with each other. And we essentially say there are no intermolecular forces, but we're forcing that by increasing the pressure. Decreasing the temperature kind of has the same effect. It makes the molecules move slower, and these molecules are going to spend time closer to each other, okay? And also in these cases, when they're getting closer together and they're not moving, then their volumes actually matter. And so we have to take that into account. And so there is a new equation, the van der Waals equation, and it looks scary. It's essentially the ideal gas law, but it's got some correction factors. Okay, and what you'll see, let me get the pointer here. What you'll see is the pressure term has a new term added to it. And what that term is, it's essentially correcting the pressure, okay? Because it's essentially dealing with intermolecular forces and repulsions. And so that is what that deals with. Now, N is the number of moles, V is the volume. The question you might have is, what is A? A is specific for the particular gas, so it's a coefficient, and this is where, again, the ideal gas law, it doesn't matter the identity of the gas. in the van der Waals equation, it actually does matter what the identity of that gas is because you need to find that coefficient. It's much less convenient. The second term, the volume term, again, we assume that the gas particles don't take up any space, but they do take up space. And so this is the number of moles multiplied by a different coefficient. And again, it is particular to the particular gas that we deal with. Now, the book, and I didn't assign any homework, but they like to assign homework with you calculating in this. I don't do that. I don't think that that's very useful. It's essentially plugging into an expression. And so this isn't a math class, but the major thing that you want to understand is why these terms are here. Again, this term here with the volume is correcting for the fact that gases actually take up space. And this term with the pressure is dealing with intermolecular attractions. And so that's kind of the key to all of that. And so again, the basic idea is that under normal circumstances, we can use the ideal gas equation and it's fine. Under certain circumstances, that doesn't work, and we do have an equation to deal with that. We're not actually going to mathematically deal with that. So this completes our discussion of gases.